All right, so 14.5, we're talking about the chain rule. And this obviously sounds familiar because you know about the chain rule from Calculus 1, something that we use when we're talking about derivatives of a composition of two functions. Um, it's the same idea here. We're looking at functions of two or three variables or more, it turns out, that are compositions of functions, but because we're looking at functions of two or more variables, exactly what a composition of functions looks like is a little bit different. So here, let's suppose that we have a function of two variables, f of x, y, and let's suppose that x and y are also functions of some third variable t. Let's just say that x is equal to g of t, y is equal to h of t. So substituting these in for the x and y here, we can write this function in the form f of g of t, h of t. Because both of these variables here, the x and the y, depend only on t, you can actually think of this entire thing as just a function of a single variable. It's the variable t. Now, the question is, how do I take something like this and differentiate it with respect to t? Well, the most direct way is to actually, if you're given g of t and h of t, substitute them directly into whatever f of x, y is. You'll get something that looks like a big function of t, and then you just differentiate it the way that you would in Calculus 1. But we want to use Calculus 3 techniques on this, and that's where the first case of what we call the chain rule comes into play. So before we do that, I want to talk about what a function like this actually looks like. If I have a function f of x, y, usually those functions give us surfaces when we graph them. By forcing x and y to become functions of the same variable t, this is putting restrictions on x and y, which means we're not getting the entire surface by placing these restrictions here. In fact, what we're doing by forcing x and y to both be functions of t, we're actually parametrizing a curve, a space curve or a plane curve. So what this is doing is it's actually taking the domain of this function and restricting it to a parametrized plane curve, which when plugged into this function is going to give us a space curve, interestingly enough. And that space curve has to live completely on the surface that would be given by this function. So if you can imagine, like, let's say, for example, that this surface gives us this function gives us like a parabola, or sorry, a paraboloid or something like that. Maybe these functions may give us some kind of a space curve that spirals around that paraboloid in some way. I don't know, but the idea is that this will give us a space curve that lives completely on this surface. And that's important for some stuff that's going to come up later in this course. We're not doing anything graphical with this in this section, so we just want to know how you differentiate a function like this with respect to the only variable that's left, the t. And that's given here in what we call the chain rule, case 1 of the chain rule. So suppose that z is equal to f of x, y, and it's a differentiable function. We defined differentiable functions in the previous section. Differentiable function of x and y, where x is equal to g of t, y is equal to h of t, like we said above. And let's suppose that both of those functions, g and h, are differentiable functions in the single variable differentiability context of t. Then z is automatically going to be a differentiable function of t as well. And dz dt is equal to the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. I want you to pay attention to which of these are partial derivatives and which of these are single variable derivatives. The d's, dz dt, dx dt, dy dt. This is saying that z, x, and y can all be thought of as functions of t, which we just kind of described why that's the case up here. F, however, can also be thought of as a function of two variables, x and y, which is why we have these partial derivatives, partial of f with respect to x, partial of f with respect to y. I'm going to talk about some ways a little bit later of memorizing the form for the chain rule. It looks a little bit complicated, but there is some patterns here that help us remember what's what. So this one we're going to prove, and then the remaining cases of the chain rule actually follow directly from this, but we're not going to make a formal argument for those. So let's begin with this assumption that the function z equals f of xy is differentiable. In the previous section, we'd said what it means for that to be differentiable. A change delta t in t produces changes in changes of delta x in x and delta y in y, and that's because x and y are both functions of t. So that's fairly straightforward. But because z is a function of x and y, creating this delta t here, which creates this delta x and delta y, these will in turn create a change in z, delta z. And from that definition in the previous section, we have that delta z can be written in this form. Partial of f with respect to x times delta x plus partial of f with respect to y delta y plus epsilon 1 delta x plus epsilon 2 delta y. In the previous section, I was referring to those epsilons as error terms. Error contributed by the change in x, error contributed by the change in y. Okay, now it's important to note that this this epsilon 1 and this epsilon 2 will both go to 0 as delta x and delta y both go to 0. That's important for this. Okay, now if we take this equation here and divide both sides by that delta t that we described at the beginning of this proof, what we end up with is a bunch of quotients. Delta z over delta t equals all this stuff. You see where the delta t's showed up. All right, now what we're going to do is let delta t go to 0, because what we want to do is take these delta z over delta t's, delta x over delta t's, all this stuff, and turn them into derivatives. They look like derivatives, but they don't have the limit applied to them that makes them derivatives. So that's what we're going to do next. We're going to take the limit as delta t goes to 0. Now, this argument here is laying out what's going to happen, but just focusing on this for a second. The delta z over delta t, the delta x over delta t, the delta y over delta t, and then these other copies of the delta x and delta y over delta t's, all of those, if you take the limit as delta t goes to 0, they become a derivative. This is the derivative of z, which is the same thing. Well, yeah, this is the derivative of z with respect to t, derivative of x with respect to t, derivative of y with respect to t, and similar here and here. So these two guys are where we're going to get this dx dt. Let me come back up here. This dx dt, this dy dt, and then we can see where the dz dt is coming from right here. Okay, but what's happening with those epsilon 1 and epsilon 2s? Well, again, we know that because x and y are both differentiable functions of t, that implies that they're continuous. And a property of continuity here would say that as delta t goes to 0, delta x will also be going to 0 with it, as will delta y. And if delta x and delta y are going to 0, we know that the epsilon 1 and epsilon 2 functions, by assumption up here, will also be going to 0. The whole point of saying all that is that these two terms go to 0. They disappear. And I'm left with that thing that looks like the chain rule. Okay? That's kind of the formal way of proving that. So down here, it just mentions that we oftentimes, instead of writing delta f, or the partial of f with respect to x, partial of y, f with respect to y, since z is equal to f in this context, we often replace those f's with z's, and we'll write it this way more often. Okay, let's take a look at an example, though. I want to take this function, z equals the square root of 1 minus x over y, and differentiate it with respect to t, where x is equal to tangent of t and y is equal to arctangent of t. So notice we have a function of two variables, x and x and y in themselves are functions of t. Okay, so there's ingredients that we need to compute for this. I need the partial of z with respect to x. That's one of the things that I need. So if I take the derivative of this guy with respect to x, we need to determine what that is. Excuse me. What would that be? So I'd be using the chain rule on this. The derivative of the inside with respect to x is going to be negative y. So I got negative y there over 2 times the square root of 1 minus xy. I'm also going to need the partial of z with respect to y. That's another necessary part of this. And I can see that this is going to look pretty similar. I'm going to end up with, let's see, the derivative of the inside. That's going to be differentiate with respect to y. That'd be negative x comes out of that. So that's negative x up here over 2 times the square root 1 minus xy. Okay? So we're kind of computing these ingredients, if you will. And then I need some derivatives here as well, dx dt of, so I need the derivative of tangent with respect to t. What's that going to be? That's secant squared of t. And then I need the derivative of y with respect to t. We need that as well. Derivative of arctangent would be 1 over 1 plus t squared. Okay? So let's see if we can put all this stuff together now. I know that from my chain rule that the derivative of z with respect to t is equal to the partial of z with respect to x times dx dt plus the partial of y with respect, partial of z with respect to y times dy dt, and we've computed all of these things. So this is equal to partial of z with respect to x, that's this guy up here, negative y over 2 square root of 1 minus xy times dx dt, which is secant squared t, and then minus, because I have my plus partial of z with respect to y, so it's going to look like minus x over 2 root 1 minus xy times 1 over 1 plus t squared. Okay? Now, you can actually leave your answer just like this. Here's kind of the interesting thing. So if you look at the answers in the book, the way that these are frequently represented, even though we're looking for the derivative of z with respect to t, other variables are actually allowed to show up in this. You see the t's showing up here and here, but we oftentimes won't substitute anything in for the x and the y. We could, but it would make this thing a lot more ugly, a lot more complicated looking. Like, for example, anywhere I see an x, I'd be substituting a tangent of t, so here and here and here. Anywhere I see a y, I'd have to substitute an arctan of t, and it ends up being very messy, and it's actually fine to leave it in this form because we have reference up here. We can tell what x and y are equal to based on what we're given in this problem. Okay, you could also factor stuff out, kind of simplify. For example, I could factor like a 1 over 2 root 1 minus xy out of everything to kind of simplify things down. I'm not super concerned with that here, but it is kind of generally good practice to do that. All right, so that's it for that first example. Now, on to case 2 of the chain rule. So as before, we're considering some function f of xy, function of two variables, and this time x and y are also going to be functions in their own right, but instead of being functions of a single variable, we're going to think of them each as a function of two variables. This occurs a lot as well. We'll encounter in chapter 16 the topic of parametric surfaces. This is very much something that we encounter when we talk about parametric surfaces. So we're looking at a function now that was originally given as a function of x and y, but can also be thought of as a function of s and t in this form. So we want to be able to differentiate this with respect to either s or t. That would be a partial derivative, since this is a function of two variables. So again, not going to prove this case, but it's actually just a direct consequence of the chain rule we've already proven. We have two versions here. One if we want to differentiate this function with respect to s, and one if we want to differentiate with respect to t, and they're given here. Notice that these chain rules look very, very similar to the original chain rule, case 1, but now everything is a partial derivative. It's all partial derivatives here. So where we originally had a dz dx, a dz dy is now partial of z with respect to x, and so on. There are a couple of ways that you can remember these. So what I like to do is I typically think of it in terms of cancellation. I think of these derivatives as fractions, the way that they're written. And I see this partial of x and partial of x canceling out. I see this partial of y and partial of y canceling out. And both of these terms now reduce to partial of z with respect to s, z over s, which is what I'm trying to find the derivative, or the partial derivative that I'm trying to find. The book also suggests this tree technique, and I've seen this tree technique used in other places as well. It's kind of useful. What we do is we construct a tree out of the variables. So z is a function of x and y. So z goes up here, and then whatever variables are acting as independent variables for that function z, we draw branches to those. So z has an x and z has a y. Those are the independent variables for this function. And then x and y independently are each functions of these other two variables, s and t. So we branch off from x and make an s and a t, branch off from y, make an s and a t. And then what we do is along the branches, we write in these derivatives that correspond to whatever branch we just talked about. So as we go from z to x, we write in the partial of z with respect to x. As we go from z to y, we write in the partial of z with respect to y. Notice from y to s, partial of y with respect to s, and so on. Then what you want to do is determine what kind of partial derivative you're looking for. So for example, do you want to find the partial derivative with respect of z with respect to t? If you do, then what you need to do is start from z and trace your way down to all of the t's that appear at the bottom here. So notice as I go from z to t, I'm going to go along this branch that says partial of z with respect to x, partial of x with respect to t. Any derivatives, any partial derivatives that I use in that path get multiplied together. Partial of z with respect to x times partial of x with respect to t. Notice that that's the first term here. And then I have to go down and find the other t as well. Along the way, I'm going to go through this branch partial of z with respect to y, partial of y with respect to t. That becomes the other term. Okay, so this little tree diagram, a lot of people like to use this to remember the order of these terms for the chain rule, and that's totally fine. It's a great way to remember that as well. Okay. Let's go ahead and try an example where we want to find partial derivatives of this function here. Z is equal to tangent of u over v, and u is equal to 2s plus 3t. V is equal to 3s plus or minus 2t. So u and v are each functions of two other variables, s and t. Okay, so we need to compute some ingredients here. I'm going to need the partial derivative of z with respect to u as one of the things. I'm going to have to do that here. That's easy enough to do. That comes out to 1 over v secant squared u over v. I'm also going to need the partial of z with respect to v. Okay, and again, that's easy enough to do. That comes out to negative 1 over v squared secant of u over v squared. There we go. Okay. Now I'm going to need partials of my u and my v with respect to all of the variables contained within those. So what is the partial of u with respect to s, for example? It's very easy. This is a nice linear equation here, a linear expression, so that just ends up being 2. What is the partial of u with respect to t? Looks like that would be 3. What's the partial of v with respect to s? Okay, here's v, so that would be 3. And what is my partial of v with respect to t? Okay, that would be negative 2. Those were all really straightforward ones. So now we need to find partial of z with respect to s. That's one of the two things that we're asked to find. Okay. According to the chain rule, what we need to do is find the partial of z with respect to u, which is given here, 1 over v secant squared of u over v, and multiply that to the partial of u with respect to s. That would be 2. So if I multiply by 2, let me put the 2 up here. Okay? And then we need to add the partial of z with respect to... sorry, which one are we doing? We're doing with respect to s. Partial of z with respect to v, which looks like minus 1 over v squared secant squared of u over v, and multiply that to the partial of v with respect to s, which is 3. So let me put the 3 here. Okay? And again, you can simplify by factoring out the secant squared of u over v if you want. What about the other partial derivative that we need to find? Partial of z with respect to t. So now we need the partial of z with respect to u, again, which is 1 over v secant squared of u over v. And this time, instead of multiplying by partial of u with respect to s, it's the partial of u with respect to t. That's equal to 3. Okay, so we get a 3 there. And then we multiply by this partial here. Again, minus 1 over v squared secant squared of u over v, and we multiply that to the partial of v with respect to t, which is negative 2. So multiplying by a negative will actually make this plus, and then 2 goes there. Okay? They look complicated, but it's really just figuring out each individual ingredient and plugging it in where the chain rule is telling us to plug it in. All right. Pretty good. So, naturally, as you may have guessed, there is a generalization to all of this. And we can talk about a function of any number of variables, and all of those variables can be functions of any other number of variables. So suppose u is a differentiable function of the n variables, x1 through xn. And let's suppose that each of these x's here is a differentiable function of the m variables, t1 through tm. Then we're going to have a whole bunch of different chain rules that we could consider here. And the general case, if I want to find the partial derivative of u with respect to one of these t's here, call it ti, then notice what this looks like. It's the partial of u with respect to x1 times the partial of x1 times with respect to the partial of ti. Notice what's happening here. Again, if you think of these as fractions, the partial or the x1s here can kind of like cancel out, and the result matches what you're looking at here. But you have to do that for x1, x2, all the way through xn until you've done all of the variables that u was originally defined in terms of. Okay? So let's take a look at an example where we need this. This is an example that you're going to do in your homework. This is just part of it. It's not the whole thing. I'm given this function n. It's a function of 3 variables, p, q, and r. N is equal to p plus q over p plus r. And then p, q, and r are all given in terms of u, v, and w. So p is equal to u plus vw, q is equal to v plus uw, r is equal to w plus uv. I'm only going to find one of those partial derivatives here. I want to find the partial of n with respect to u. Okay, so what do we need in order to do that? Well, I need the partial of n with respect to each one of these variables. So p, what is that? For this, I would have to use my quotient rule because p is showing up in my numerator and my denominator here. So what would that be? That would be p plus r minus p minus q is what that ends up being, over p plus r squared. This ends up looking like r minus q over p plus r squared. Okay, I also need my partial of n with respect to q. So for that one, that's pretty straightforward. That actually just comes out to 1 over p plus r. I'm also going to need my partial of n with respect to the last guy, which was r. Okay, and that's going to equal negative p plus q over p plus r squared. Okay. Next up, I need the partials of p, q, and r all with respect to u specifically. So what is the partial of p with respect to u? Well, that's going to be 1. What is the partial of p, not p, we just did p, q with respect to u? That's equal to w. You can see where that would show up here. Partial of r with respect to u, what's that going to be? V. Okay? Now we're going to put all this stuff together. And the way I lined things up here are the way we're going to multiply those terms. So notice I have a partial of n with respect to p, partial of p with respect to u. These two terms have to get multiplied together. 1 times this. So what am I going to get? Partial of n with respect to u is equal to 1 times this, which is just r minus q over p plus r squared. Then I have to multiply these two and add the result, plus w over p plus r is what that would look like. Oh, I just realized I'm off the screen. I feel like I do that a lot. And then I have to multiply these two guys, which is going to be minus v times p plus r, or q, that's a q there, all over p plus r squared. And yeah, there's simplifying that we could do. We can combine stuff, but I'm not concerned with the algebra that follows from this. I would just call it a day at that point. Okay, and again, you're getting a mix of these different variables. You're getting a mix of the p, q, and r, and you're also getting a mix of the u, v, and w. The u's not making an appearance, and that's just because that's how the derivatives worked out. But it's possible in a different case that the u might have shown up. Okay, we have a little bit more to talk about, but we'll do that in the next video.